So we are moving for the next presentation. Next presenter. Is Ivana Stanicic. Can you share your presentation, please?
Yes.
Hello. Hello, Ivana.
Can you hear me?
Yeah.
Good.
Ivana Stanicic is a postdoctoral researcher at the Division of Energy Technology at Chalmers University of Technology, and her research focus on trace components in chemical looping processes, and more specifically examining the fate and impact of ash components in this type of technology. So whenever you want, Ivana.
Thank you. Professor Zhao Ming, could you please stop sharing? Thank you very much. Now I think we are set. Thank you very much for the introduction, and thank you also for inviting me to this workshop to hold this presentation. Thank you to the previous speakers as well for introducing the field of gasification, also for introducing chemical looping gasification. So I will be following up on that, and my presentation will focus specifically on the role of ash chemistry in chemical looping gasification. And CLG has emerged as a promising technology for converting challenging fuels like microalgae. And so understanding the interaction between biomass or biofuels and interactions between ashes and oxygen carriers become important in these type of systems. And yeah, because these ash-related issues can significantly impact the performance, and particularly when using very complex fuels. So today I will be going through why ash is important in chemical looping processes, some of the key components in biomass fuels, and also how that relates to microalgae specifically. Then I will show some preliminary results on what could happen when utilizing microalgae in chemical looping processes, and also go through some of the expected challenges that one could encounter, and also how to mitigate or have some strategies for enhancing the performance, and then end up with some future perspectives on that. So let's start. Why are ash interactions important at all? Because ash doesn't have any calorific value, but it does influence our process efficiencies. And it could, in some worst case, lead to economic losses because it can induce very harsh environments in our boilers. And this is specifically important when we talk about very impure fuels. So I'll go through some of the negative effects that that could have. And one of the major ash-related issues, especially in relation to biomass fuels and waste-derived fuels, are the negative effects that has to do with ash compounds, usually in the form of different alkali silicates that melt and coat our oxygen carrier particles. And when this melt fraction increases, it could capture a lot of these particles and result in agglomeration. And that could be quite negative if it results in defluidization of our bed. And just to show you some previous experience that we have had with that. So in this picture here, we can see an agglomerate. And these round particles here are oxygen carrier particles. This is a picture taken with scanning electron microscopy. And it's a cut through to see how the cross section of these type of agglomerates look like. And here in the middle, we have a melt. And as I said before, defluidization it could typically occur due to the very complex composition of fuels. And typically in high temperature processes, these problems are related to alkali silicates, which form because they have low melting temperatures. And so what happens is like they melt and cluster our particles together as shown in this picture here. So this is from a batch scale experiment that we have observed this, but this has also been observed in industrial settings. So what we see in this picture here is a chunk that has been obtained from combustion of municipal solid waste in fluidized beds, where we have a melt present and a lot of oxygen carrier particles being adhered to the surface of this melt. So this is what it could look like. Another way for this to happen is also through sticky phosphorus compounds. And here we have also seen that we can have oxygen carrier particles, as shown here in these two round spots here, being coated with a phosphorus containing layer. So this is another way to induce agglomeration. The second impact that ash can have is fouling and corrosion. So we can have ash being present in our gas, which can condensate directly into cold heat exchanger surfaces and cause a melt, or it can nucleate and then condensate upon impaction. And this is especially a problem in waste to energy plants because we have very harsh environments. Because we can have a mixture of both alkali and metal chlorides in our gas. And this mixture is especially troublesome because it has very low melting temperatures and could, when it's deposited on our heat exchanger surfaces, increase the corrosion rate. And yeah, it could lead to some operational issues that can be quite expensive to deal with. But let's not only talk about the negative effects that we have here. We should also acknowledge some of the positive influences that our oxygen or ash components can have on the process. So one of the more common ash components, such as calcium, that's usually present in our fuels, can act as catalyst for gasification reactors and improve the yield. So there is that aspect as well. And how can we influence our process? There are several factors that come into play here. And usually they are a combination of both physical and chemical factors. So we have the fuel characteristics, size, shape, and composition. We have the operational mode, whether we are combusting, gasifying, or pyrolyzing our fuel. And then also, of course, the temperature and pressure. One thing that we can affect a lot is the selection of an oxygen carrier, which sets the chemical surroundings in our boilers. And here also ash composition is one of those factors that influence a lot. But here in this case, we have gasification of microalgae, which sets the conditions for this specific type of work here. So I will focus more on that. But first, if we consider this scale, determining the complexity of different fuels, we would have gaseous fuels far to the left. But if we are looking at solid fuels, we do have a lot of experience with wood chips, which I would put here far to the left. Yes. And then a step further into complexity, we can find, for example, demolition wood, which contains slightly more type of impurities and other ash components. And then more to the right on this type of scale, we have waste-derived fuels, which can contain almost the whole periodic system. But today we are focusing on a new type of fuel. So how does microalgae come into play here? And how can we use our previous experience to see what would happen and what we can expect in our type of boilers? So here I've listed the key components in these biomass fuels. We have wood chips, demolition wood, and municipal solid waste. So we have the volatiles, the fixed carbon, moisture, and ash. So here we can see when we add the microalgae here, how it relates to the other type of fuels. So we see we have slightly more moisture being present. This can have some impact on performance and decrease the efficiency, as we have to have slightly higher energy consumption for drying. We also have slightly lower fixed carbon compared to other fuels. But then if we look at the ash content also, it's comparable to that of demolition wood. So it's slightly lower than demolition wood, but slightly higher or higher than wood chips. So I would put the fuel somewhere in between here in the complexity scale. But this means that we would likely need some handling of these solid residues after the process. So let's take a look at what this ash actually contains and how that relates to these other type of biomass fuels. So here we have, I'm showing the ash composition for these different type of fuels. We have calcium, potassium, and silicon dioxide being the more common components. The fraction here that is where I didn't put anything, it's other type of components present. And if we take a look at microalgae, we see a slightly different composition. We have more sodium oxides compared to the other fuels. We have quite a lot of potassium and phosphorus as well, but much less silicon and calcium. So as you remember maybe previously in the first slides when I talked about different types of problems we could have, both alkali metals and phosphorus were shown to maybe cause problems and coat our particles. So would this be a problem? Not necessarily. And there are some benefits with having this type of composition as well, because we have quite low silicon content, meaning that we have a lower risk for forming these sticky compounds. And also alkalis on oxygen carrier surfaces could have a positive effect with respect to gasification. But how could these components interact with our oxygen carrier then? So I made a quick study of this to look at possible interaction pathways for different components and their influence on operation based on experience from other fuels and other oxygen carrier ash interactions. Here I will focus on potassium, sodium, and phosphorus. And I have been looking at studying these type of elements under gasification conditions at around 800 degrees. So what we can find looking at potassium, probably we would find some potassium hydroxides and minor amounts of chlorides in the gas phase. Due to the high concentration of phosphorus, we probably would have some potassium phosphates as a solid. And looking at the experiences that we have, the interactions with oxygen carriers could lead to potassium iron oxides, potassium titanates, and potassium silicates. And I put others here because there are probably some other compounds that we haven't investigated, or different type of oxygen carriers that I haven't been focusing on here. Looking at sodium, similar thing can be observed here. Hydroxides, chlorides in the gas, and then some phosphates in the solids phase. Here, it's possible that we form some sodium iron oxides and sodium silicates through interaction with oxygen carriers. And lastly, we have the phosphorus being present as alkali phosphates. And here, there are also possibilities for forming calcium phosphates as a result of interaction, which could cause the surface coating that we have observed in batch scale experiments previously. But what about calcium? Because it's usually one of the major elements in biomass ashes, and it's known as, has been pointed out in the previous presentations, it can have some catalytic effects. It could also prevent melts in our process. It could potentially interact with phosphorus also to form non-sticky compounds, but these could also coat the oxygen carrier particles. But we see that we have low levels in microalgae ashes. So what could we do then? We could co-gasify it with other biomass fuels or use additives. We can look at different operating temperatures or pre-treatment of fuels, but we can also select an appropriate oxygen carrier, which is probably the easiest pathway to go. So oxygen carriers in chemical looping gasification usually have limited oxygen transfer capability, but the oxygen is most commonly transferred using iron as the main component. And then there are many different types of oxygen carriers that can be used. One of the more investigated ones are the mineral ores. They usually contain iron and then some other type of components, titanium, for example, and then smaller amounts of calcium and manganese. Here we have some examples on ilmenite, tierga ore, and manganese ore that Daofeng also talked about. And titanium is good for capturing potassium in these processes. And then we could also have possible reactions with iron and manganese if we select one of these type of mineral ores. But then we also have waste byproducts. And these usually contain a limited amount of iron, but also much more calcium and silicone. And here we have, for example, iron sand and LD slag as examples. And iron sand is an iron silicate oxide, so it contains quite a lot of silicone, and that can be good also for limiting the release of potassium into the gas. And then LD slag contains quite a lot of calcium as well, so that could be good for capturing phosphorus, reduce melt formation, and possibly also improve gasification conditions. So if we take a look at the future perspectives, we can see here some of the challenges that could be expected since we have high levels of alkali metals in the ashes, and some phosphates also could potentially have some problems related to agglomeration or corrosion. But we have an opportunity by introducing an oxygen carrier to bind these alkali metals and mitigate this. But then also there are quite limited studies on interactions with sodium, phosphorus, and oxygen carriers, in contrast to those that exist in relation to potassium and oxygen carriers. Then it could also, I think, be interesting to look into the development of processes that enables recovery of valuable nutrients, such as phosphorus, which is one of the major elements here in microalgae. So I think microalgae holds a potential for third generation production of biofuels in chemical looping gasification. And this is just a part of a larger puzzle. And chemical looping technologies can actually help us to reach the climate goals and reduce emissions. And the role of microalgae chemical looping gasification could contribute to a more circular economy by providing sustainable fuels. And by understanding the complexity of these technologies and exploring new pathways for biofuel production, we are one step closer to achieving a more sustainable fuel. So thank you very much for listening.
Thank you very much, Ivana, for this interesting talk. We have time for some questions. So if anyone in the audience has any question, please. Uh, so I have a question just for you. According with your experience, maybe with ilmenite, that is the most common acid carrier used in chemical looping gasification. Do you think that could be a problem with the use of microalgae, according to the
And I
possible?
think the good thing with ilmenite is that it can capture potassium. So I
Yeah.
think it could have very good properties with respect to that. And then I guess the remaining thing that we have seen regarding sodium and phosphate is that it could coat the particles. I don't see a specific issue with utilizing it. I think it could have good properties.
I think we probably could have problem with this iron sign. It has a lot of silicon. So you mentioned that silicon can like react with sodium, potassium, I think, right?
Yes, yes.
So that could cause something like melts, and then
If silica is freely available in the sample and not bounded as an iron silicate,
Mhm.
it could lead to some melting. But if it's bound as an iron silicate, I think there are lower risks for that
Okay.
happening.
Yeah. Good.
Okay, thank you very much, Ivana.
Thank you.
I think according to the timing, there is a small coffee break, so maybe we can continue in 10 minutes at 11. We continue with the talk of Sylvia.
Okay. Sounds good.
Okay.